Good morning. So this talk is about the development of a numerical prediction method for the strain energy density in welded joints, starting from nodal forces. Allow me to introduce myself. My name is Simone Lucertini. I have a double identity. I mean, I am a PhD student on University of Perugia. This is my first year, and this is my very first international conference. But at the same time, I work for a company, an USA-based company, which is Terex. And in particular, I work for GE, where in Italy, we designed with this kind of machine. There's a mobile elevator working platform, and my role is design engineer principal. Today we're going to talk and focus about welded joints for steel that are subject to high cycle fatigue and for complex welded structure for large scale models, and that's the key. So it's a sort of big data analysis because it changes the way we analyze welded joints. So we have a dual vision of the welded joint analysis. One is about research, state of the art, one is about industrial, state of the art. For the research standpoint, we have a lot of interesting theories and application. Those are innovative methods, very promising and sometimes very, very accurate compared to physical tests, but usually are adapted for small scale application or simple application. On the other hand, industries still use the regulation. For example, in our field, the EN 30001, but you might know the ER 3, or the British standards and 608. Those are using or the nominal stress method or the hotspot method, which are very consolidated and works well, and they are applicable in large scale. They are easy to apply to large numbers of joints. But your joint has to be inside a classification, so the shape, the geometrical features has to match the one represented by the classes, and so the loads and the direction of the load. So we are trying to merge those two words inside a single method that can do the benefits of both. So the objective is to elaborate a new applicative method for fatigue prediction, or what the joint course, that incorporates these new techniques from research into industrial large-scale models. And as a boundary, we want to obtain an optimized balance between the reliability, the accuracy and precision of our results, and on the other hand, the computational speed. So we can use this method both for design and validation stages. So briefly, the steps we're going to follow is to go for a reference theory of the method that we are using, and introduction of this method and its calibration. Then I show some test cases to validate it, which is the operational workflow for the designer who is going to use this tool in the field, and some results together. For the theory, one of the most interesting methods that exist and recently have been developed is the average strain energy density criteria, or ASED. It's an energetic local approach that this is an example of a welded joints seen in plane as slides. And in this small radius, this criteria tells to gather the energy, or better, the energy density on this area, which is, of course, a volume, the third dimension. The R0 has this complex formulation, but for the nominal welded joint, in this case, the angle is known. R0 is just a metal of the material. For the steel, the value is 0.28 millimeters. So that means that gathering the strain energy density, the average strain energy density in this here, and this value here, and comparing to a limit one, it is optional to predict the crack initiation. Sorry. Okay. This method has a lot of pros. So it's applicable for FDA, which is good for companies. Its accuracy has been proven by hundreds of physical tests. Virtually can describe any joint shape, and it's based on a solid physical quantity, which is the energy density. So it has a strong academic concept. But for application, is complicated. It requires an extra fine mesh on that small volume, so it is usable mostly as validation of viewpoints. In all it takes in account brick elements, so solid mesh elements, and it requires a high computational effort to the high number of elements, and also a dedicated intense pre-processing to create the volume and the mesh refinement required. As well, the post-processing is not that simple too. On the other hand, for the industry application, one of the methods that works and is incorporated in some commercial software is the structural stresses from nodal loads. You might find it with different names, so it's sometimes difficult to find papers about that. But generally, this starts with a shell representation of your welded joint. And if we want to analyze the threads on the weld line, this is a mesh-insensitive approach, so it requires just a quartz mesh, a very simple model. So from these forces here that any FEA solver can retrieve, it is possible to distribute them based on the length of each specific element edge. With this formula, basically you can retrieve a distributed load, which can be a force or a moment, and retrieve the stress at the weld toe just as a combination of a pure tension or compression component plus a bending component. These approaches are a lot of pros, so it's again applicable for FEA. It's useful for validation and design for brick and shell elements. It do not require pre-processing. In fact, these commercial software are post-processors, so it takes low computational effort, so you can calculate hundreds of joints in few minutes. So it's accepted by industries and in automotive. As concept as some approximation, it takes into account only some loads. The welding is simplified, it's not. We want to merge those two methods together. So this is a core section of L-shaped joint. So if you want to analyze what happens here at this weld toe, by applying different forces and moments of the loads in the near and the far section, having this boundary condition constraint, we observe that basically the strain energy density here depends only on this close to this section, this area, and it's independent from the other. This means that we can somehow correlate the local loads, forces, and moments to the strain energy density. So it's something that we can do. So the idea is to convert this complicated model on your left, which is just a section where you can imagine a more complicated welded joint with this processing to create the volume and split the solid to have a better mesh, to the model on the right, which is a very simplified model using shells and applying and considering the loads within the weld. So, of course, in the shells, you don't have information to the strain energy density on that area. So it is required to calibrate this model to correlate different kind of geometries and different type of loads. So how do we calibrate? For example, for an L-shaped joint, the strain energy density method that we consider now as a reference, the full model requires to change the geometry every time we change, for example, the thickness of the connected plate. So we have to change the geometry, the mesh, and we run the entire analysis. Then we get directly the strain energy density from that. In the proposed model, accepting a small error, we use only one shell model for all the thicknesses, since the thickness of the plates is changed analytically. The small error is due to the fact that changing the thickness, we should correct the position of the weld toe a little bit, but we don't accepting a this error with the benefit to having a unique geometrical model describing multiple thicknesses. This model gives us forces and moments. So from that, we should use some other tools, in my case, Python, to calculate the stresses from the loads and then estimate the energy. Of course, we are going to need a compensation factor XC that will depend from the core section geometry and from the thickness of course, when the weld size has just a minor influence on that. That means that the reference model above, the full-scale model, and our proposed model below are connected together this way. So from the one above, splitting the weld path, we retrieve the strain energy density, which is not constant within the weld path, of course, and this is directly retrieved by FPA software. While again, from FPA software, we retrieve the nodal loads on the simplified model as just tables or numerical values, and then we process them. Here it is the point. We cannot correlate directly the stresses to an energy. They have different units, they are different things. So we square the terms and divide it by 2 times the Young modulus. That means that this has the unit of an energy, it's a pseudo energy. Again, we need a compensation factor, but now we are comparing apples to apples. So, this correction factor, of course, is not constant. Otherwise, the estimator will say the same thing. It will be something the same matter. It's changing depending on the plate thickness. Actually, the company interest was for sizes between 3 millimeters to 6 millimeters, but of course, this analysis can be extended more. And comparing the results using this correction factor, which is more or less linear, we got these results, which are the solid lines are the reference to the full-scale model, and the dashed lines are the simplified model's prediction of the strain energy density. And we see a promising correlation, a good correlation between our prediction, and also including the edge effect and the mid-plane effect. So we can say that it is valuable as a comparison. So this process is called background calibration because we obtain this curve which is provided to the design engineer. So it's not required to do this calibration for applying this method. Validation. Is this working? Well, it happens if we change the geometry, we apply to another joint with different shapes, boundary conditions, loads. So we applied, for example, to a tube welded on a square plate, and I'm presenting just a demonstration today, but we changed also the dimension of all the elements. We did an analysis of sensitivity. So the full model above and the simplified model below with shells, applying the same compensation factor we saw before with completely different geometry. It was an L shape with bending moments. And this is a completely different situation. We have a very strong correlation, especially in the middle, where the difference is very, very tiny, 2–3%. Well, at the edges, we have a little bit more error, but in the various files, we have something which is beyond 7%, more or less, using, as I said, the same coefficient from the calibration. So we change the global shape, we change the load type, intensity, and also the boundary condition, but the correlation seems promising, seems great. Operatively, how it is applicable in the industry? 2 ways, of course. The first one is just using the script for full control. In this case, it's Python, as I said. Or I also included this same script inside a visual tool, so it's easier for non-expert user to set up a workflow and do their calculation without any coding or coding ability. This also has been included in the new package by ANSYS, which includes this library, which is PyDF4, that allows us to get the results from an ANSYS analysis or an RST file, get all the results we want, process the results as we want, and project those results to a geometry. So we can also visualize our results over a geometry. This is just an example, but you can do that for a very complicated geometry. So just for representation, for displaying and showing the results. Going to conclusion, so we got a promising correlation between the elemental model loads forces on a simplified shell models and the full-scale 3D model for the strain energy density. So obtaining a method that, if developed, could grant is applicable as FEA post-processing as the industry one. It also works for design and validation. Design because it's easy to iterate with different thicknesses. For example, the system is super fast. It uses open source tools like Python and other free libraries. It's a good compromise in terms of accuracy and power consumption and CPU consumption. It virtually can describe any brain shape, any global loop type direction with a very low computational effort, as you say. So it is possible to apply this method in large scale applications where you have hundreds of joints that you need to analyze in quick times. Just 30 seconds ongoing development. So we want to test, of course, more validation cases and implement other core types, extend the application to more complicated 3D weld paths, and to continue integrating with our finances and our library to have a seamless tool for the designer. Then separate the energy components for strain or stress just to understand which component is most important for the energy, and extend it out and include some automations and optimization to for help the designers. Thank you.